Ocean acidification is a process driven by increased carbon dioxide, CO2, emissions in the atmosphere, leading to the absorption of CO2 by the oceans. Here's an overview of the science behind ocean acidification. Carbon dioxide absorption. The world's oceans act as a sink for CO2 emissions from human activities, including burning fossil fuels, deforestation, and industrial processes. As CO2 dissolves in seawater, it undergoes chemical reactions that increase the concentration of hydrogen ions, H+, decreasing pH levels and making seawater more acidic. pH and acidity. pH is a measure of the acidity or alkalinity of a solution, with values below 7 indicating acidity. Ocean acidification involves a gradual decrease in pH levels, shifting seawater towards acidity. Since the beginning of the Industrial Revolution, ocean surface pH has decreased by approximately 0.1 units, corresponding to a 30% increase in acidity. Carbonate ion availability. Ocean acidification reduces the concentration of carbonate ions, CO3 to the power of 2, which are essential building blocks for marine organisms to form calcium carbonate structures like shells, skeletons, and coral reefs. Reduced carbonate ion availability makes it more difficult for marine organisms to maintain these structures, impacting their growth, reproduction, and overall health. Impacts on marine life. Ocean acidification affects a wide range of marine organisms, including calcifying organisms, shell-forming mollusks, e.g., oysters, clams, crustaceans, e.g., crabs, lobsters, and coral reef-building corals struggle to build and maintain calcium carbonate structures in more acidic conditions. Plankton and primary producers. Phytoplankton and zooplankton at the base of marine food webs may experience altered growth rates and ecosystem dynamics. Fish and marine ecosystems. Acidification effects can propagate through marine food webs, impacting fish populations, biodiversity, and ecosystem resilience. Ecological and economic implications. Ocean acidification poses significant ecological and economic challenges. Threats to coral reefs and marine biodiversity jeopardize fisheries, coastal protection, and tourism revenues in many regions. Changes in ocean chemistry can disrupt marine ecosystems and alter nutrient cycles, affecting global biogeochemical processes and climate regulation. Monitoring and mitigation. Monitoring programs track ocean pH levels and carbonate chemistry changes in different regions to assess impacts on marine ecosystems and species. Mitigation strategies include reducing CO2 emissions, promoting sustainable fisheries and aquaculture practices, and supporting marine conservation efforts to enhance ecosystem resilience. Understanding the science behind ocean acidification underscores its complex interactions with climate change and its profound implications for marine ecosystems, biodiversity, and human societies dependent on marine resources. Addressing ocean acidification requires global efforts to reduce CO2 emissions and protect vulnerable marine environments through informed policy, research, and conservation initiatives.